Hey everyone, it's Dr. Calkins, week 16, chapter 11, last chapter of the semester with gases and pressure. So very different than the Queen song, this pressure, we'll talk about first its units and then define it with respect to volume, temperature, and number of moles. Notice mole being the big concept in exam 5, as well as mole conversions. So when we think about pressure, we have to think about the force that it exerts on the container. So as these molecules bounce around inside a container, you can add pressure by adding molecules, just like deflating a tire if you have a leak and molecules are no longer in the tire but in the atmosphere outside the tire, then it goes flat, that kind of idea. So those are ideas we'll talk about. But that force that exerts on the container is what we're after and how it changes. One way to measure pressure in your tire would be PSI. Other ways that you might measure pressure would be barometric pressure, say in the news. So what we typically deal with in chemistry is 1 atmosphere. That's just our normal standard unit. It's equivalent to 760 torr, named after Torricelli, the scientist that came up with the first barometer. One of the few lady scientists we get to talk about. They eventually converted that to millimeters of mercury. So if you watch the news in Canada or Mexico or somewhere else other than the United States, that's what they would probably mention. In reality, they'll probably mention 76 centimeters of mercury instead. In the United States, they're going to measure it in 29.9 inches of mercury because we're different. And we use our English system still. Also, about 14.7 psi, a lot of tires contain about double that. So we need to be at a stronger pressure than the atmosphere or we're not inflated for a tire or basketball or whatever. So those are conversions. So you could pick any one of these. So if you had, let's say, 30.1 inches of mercury in the atmosphere on the news, say it's before, after storm, whatever, you can get rid of inches of mercury by putting it on the bottom. And we know that for every 29.9, that's 1 atmosphere, or if we wanted to convert to anything else, we could. So then that's just division, 30.1 divided by 29.9, and that tells us it's about 1.01 atmospheres. So that's the typical kind of conversion you'll see early in the homework. Not meant to be difficult, it's meant to be a shout out back to the metric system and those kinds of conversions we saw previously. Another thing we need to talk about, at least conceptually before we cover the mathematics of this chapter in a separate video, is just the relationship of pressure when it changes and how it changes, who it's related to inversely and proportionally to. So let's try to build what we call the ideal gas equation. So let's look first at pressure versus volume. So P versus V. So when you think about this, you might think about kids in the playground. So if you have kids in the playground at recess, let's say they're 3rd graders, 4th graders, doesn't matter. So 4th graders are at a recess, those little kids are running across the playground, bouncing off all the walls, just like molecules in a container, whether it be a tire or a basketball or a balloon or whatever. So given the volume of the playground, the pressure is equivalent to the number of kids out there, the temperature that those kids are playing, and so forth. So what if Johnny pukes on the slide, and now the teachers quarantine off this part of the playground? What's going to happen to the pressure? Well, now, because our volume is now less, those kids are going to be quicker to run across the playground because the playground is smaller, and the pressure is going to go up. So if the volume went down because we isolated off a part of the playground that's got puke on the slide or whatever, now our pressure is going to go up. This is what it means to be inversely proportional. So as one goes up, the other goes down. So if the playground is smaller, the pressure goes up. As long as the number of kids stays the same and the temperature stays the same, that's going to be what happens as a result. You can imagine the same thing to happen if those kids are on the playground and they're running across the playground, they have a certain amount of pressure on all the toys and the swings and the slides. But now, because it's a nice day and it hasn't rained in a while, they allow the kids to play in the field next to the original playground. Now it's going to take those kids twice as long to run across this new field. That's going to reduce the pressure. So notice now when we think of pressure versus volume, the volume went up, it doubled. That's going to cut the pressure in half. That's again inversely proportional in both situations. Again, assuming that the kids stay the same in number and that the temperature didn't change. So that's how pressure and volume are related. If we think about it in an equation, pressure is on top, volume is on bottom. So this would be inversely related, and this would be proportional. So we'll come back to that as we talk about other examples here in a minute. So let's try another one. Kids in the playground analogy works pretty well. Let's think about pressure versus temperature. So in the summertime, kids are in a playground, molecules are in a container, and the sun's out. So the sun heats up those molecules and they move very fast because they're very hot. Just imagine kids with shorts on and tank tops on. They're going to run across the playground very quick because it's very warm outside. But imagine that speed they are at is specific to the number of kids out there, to the volume of the playground. We're assuming those things don't change. But now let's take that exact same playground, even though the sun might be out. Now let's say, instead of stars, these are snowflakes. Now it's really cold. So here it was hot, here it was cold. Now there's snow and ice on the playground. Now those kids in the playground are going to move much, much slower across the playground. This is no different than what happens to a basketball in the wintertime when you leave it outside. It feels like it's flat. It's not because the basketball feels like it has a hole in it, it's because the pressure is now diminished because the molecules are moving slower. Because over here the kids were in these t-shirts and shorts. Over here the kids are in coveralls. They can't barely move. They're like that kid in the Christmas Story. They can't even walk because they're wearing so many layers of clothing because they're so cold. So here, cold means slow. That means low pressure. So low pressure, but also low temperature. Over here, cold means fast molecules or fast kids on the playground. That's going to be high pressure, and that's going to be a high temperature. So no different than throwing, say, something that is aerosolized into a fire. You heat up that canister, whether it's a can of hairspray or whatever, it gets so hot so fast that eventually has more pressure than the container can hold and it blows up. And that's all based on this idea of, are those molecules moving fast when it's warm or slow when it's cold? You can put a balloon in a ice machine, it's going to shrink. And the reason it's going to shrink is because those molecules move slower when that happens. So this is what we mean by directly proportional. And if it's directly proportional, we can put temperature on top of our equation. Another one that we need to talk about is number of molecules or number of children on the playground. So that's pressure versus N. N is moles. Moles are molecules, same idea. Avogadro is the one that helps with this. Charles and Boyle were the scientists that helped us with the other two. So in this situation, think of your kids in the playground, and we'll just do dots. We have the whole third grade out there. So all of those guys are moving around, causing pressure. But let's say this is third grade at recess. Maybe it's fun day, and now third and fourth grade are out there at the same time. So now there's twice as many kids, which means twice as much pressure because they're going to bounce into each other as well as the container. So more molecules, so more moles equals more pressure. Should be the most no duh of the bunch. If you add more air to your tire, it inflates. It has more pressure inside of it. So this is what we also mean by directly proportional. More molecules, more pressure, just like higher temperature, more pressure, but volume and pressure, those are opposites. So we can put N up top. So all we need left is a way to relate pressure, moles, temperature, and volume together. Pressure is an atmosphere. If it's not, you have to convert. And there's lots of conversions that we talk about up here in order to get to atmospheres if you need it. N is in moles. If they give you grams, you can use the periodic table to convert to moles. That was molar mass. Temperature has to be in Kelvin. If it's in Celsius, you have to add 273. Volume is in liters. If it's in milliliters, you're going to have to divide by 1,000 to get to liters. So we need a way to get those units canceled so we can do conversion processes, and that's why we get the magic number R. It's kind of like pi in math. This is the magic number for gases. This is called the ideal gas constant. 0.0821 liters times atmospheres over moles times Kelvin is the magic number. So this will cancel liters, it'll cancel atmospheres, it'll cancel moles, it'll cancel Kelvin. So this is the number that all gases have in common with those specific units. It's the way nature created. So scientists test lots of gases and they all have this number in common, and we'll use that number in a separate video to do mathematical problems because that's all that's left in this chapter in this semester. So we'll come back to that.